So, welcome student to this nonlinear introduction to nonlinear optics course. So, before going to the nonlinear optics, first we learn few basic things. We called it the basic optics or basic linear optics. So, today is the lecture number 4. So, we continue with our basic linear optics. In the last class, we have learned something about anisotropic medium. So, today we will continue with the anisotropic media and learn few more things on anisotropic medium, how the electric field and the propagation vector E are related to each other, how D and E, these two vectors are related to each other, that we will going to learn with all mathematical derivations. Okay, so let us start with this old picture. This picture is not a very new thing, because in the last class we have used this picture, which suggests that in anisotropic medium how the electric field D, the propagation constant vector k, the magnetic field H and the Poynting vector S are related to each other. So, quite interesting things are there. The picture is quite simple, but let me remind you how these things are coming. First, we learned this equation number 1, whatever is given here, that D is equal to epsilon bar E. That means D and E are not parallel. That is the most important thing here. Then we learned K and D are related with K dot D is equal to 0. That means K and D are perpendicular to each other. If you look this figure, whatever the figure is given in this slide, you will find that K and D are perpendicular, no problem with that. D and E are not parallel to each other, that means D and E are not collinear, that means they have different direction. So, these are the vectors and they should have different direction. Here in the figure we find that D in one direction and E is another direction. So, there is an angle between D and E. We will come to this point in the later part. Then S is usual E cross H. All this expression is derived in anisotropic system. So, E and D relation is the most important one, which is not linear here. So, I mean linear means they are not collinear. So, they are not parallel, which is the main important thing here. Then S is equal to E cross H, which is the usual thing, and that is why S is moving in one direction and which is parallel to E, perpendicular to E, whatever the E vector we have, and the H which is perpendicular to this particular plane. So, it is perpendicular to both. So, that means it is perpendicular to the plane containing the vector E and H. And then finally, we have one important equation, which is K cross E is equal to some constant into H. All this equation is coming from Maxwell's equation. So, that means K is also perpendicular to I mean H is perpendicular to K and E. So, again H is perpendicular to the plane containing E, D, S and K. So, obviously, H will be perpendicular to K and E, which is in the same plane. Okay, this is we have already done, and one important thing is here is that K and S will be not in the same direction. That means energy flow and the direction of the propagation, energy flow and the direction of the propagation means here the wave vector is moving in one direction and the energy is moving in another direction. If I try to understand this figure, if you try to understand what is going on, then we need to look, we will need to see this figure. This figure suggests that if you look this figure suggests that the same figure, but I have some line. This is the phase bond or the wave front. So, wave front we know that it is parallel to the perpendicular to the k vector. So, that means wave front are moving in S direction, but the wave fronts are parallel to k vector. So, energy is flowing along s direction, but it is perpendicular to the k vector or the propagation constant vector. So, some sort of angle will be here between k and s. So, this angle is important, this angle is important. If I call this angle say phi, so phi is the angle between s and k, and we will learn that how this phi is important and how to determine this phi in this particular system where we have the information of the refractive index. So, that thing we will come slowly. So, here the important thing that we learn that k and s are not in the same direction, E and D are not in the same direction, but E and S are perpendicular to each other and D and K are perpendicular to each other. That means, the angle between S and K is this phi, and the angle between the vector D and E, this angle will be the same angle. Okay. So, let us go back to the next slide. Okay. So, here now we try to understand the entire picture by using the Maxwell's equation. So, these are the Maxwell's equation, two Maxwell's equation is written here, one is this and another is this. So, as I mentioned that these things are not very new, because this equation has already been derived in the previous classes, but k cross E, again I am doing this. So, k cross E is nothing but this curl cross E. I just replace this curl operator to k, that we can do, and then it is minus of del B del T, that was the original Maxwell's equation. So, this curl cross E is replaced by k, and then del T we know that is replaced by minus omega. So, there omega is there, and B is replaced because we know that B is mu 0 h. This is another relationship between mu and h. I use this relation, and this leads to the first equation. Second equation in the similar way, if I write the second equation was curl of h was equal to del D of del T. This is another Maxwell's equation, this is the fourth Maxwell's equation. So, this del D del T is replaced by epsilon omega, epsilon bar omega E, because D and E is related to for anisotropic system. We know that D vector and E vector is related to this epsilon, which is a tensor quantity. So, I use this. So, d dt is replaced by minus omega. So, this that is why minus is here, and then this is the form. Now, here it is extended epsilon, we write in the previous case, we write that epsilon is epsilon 0 into big K. So, big K is nothing but the refractive index, square of this refractive index. So, I just replace all these things and I have two equation in my hand, which is essentially the two Maxwell's equation. Now, the way we derive the wave equation, here we will do the same thing, but the treatment is slightly different. The treatment will be, in that case we just operate curl over curl. Here we will do the same thing, we will operate k over k. So, if I make a cross product of this equation, both the side, this is, suppose this is my equation 1, if I make a cross product of equation 1, then I will have these things. So, mu 0 omega will be as usual, h will be there, and k cross h term will come, because I am making a cross product entire equation with k. Then k cross h, I will use the equation 2 information from equation 2, I will replace, and I will have that k cross h can be replaced by minus epsilon 0 omega k double bar e. So, I will replace this 1 omega and mu is there. So, you will have this omega square and mu term. So, finally, this term leads to this. omega square mu 0 epsilon 0 k bar bar E. After having that, we can expand this k cross E like we expand A cross B cross C. So, we know the rule is A cross B cross C is B C A minus C A B. If I do this straightforward vector rule, then we have these things will be simply equal to k and then k dot E minus k square, which is nothing but the k dot k and then E. So, in the right hand side we have omega square divided by c square, because mu 0 epsilon 0 is nothing but 1 by c square. So, we have omega square c square k bar bar E. So, we have an equation in our hand. This equation is nothing but the straightforward wave equation, but in different form, in the form of k. In that case it was in with the operator, but as if we are doing the same thing in Fourier space. So, we have k in our hand instead of having the del square or del operator. Here one interesting thing is also there, that k dot E in anisotropic system is not equal to 0. In isotropic system k and E is 0, but k dot E in anisotropic system is not equal to 0. So, obviously that produce some extra effect, that is interesting, that k dot E, if k dot E equal to 0, then this term was not there, this term was not there, and we will have an equation equivalent to the wave equation that we have in our previous case. But here we find that k dot E is not equal to 0. So, that means some extra will come here. Okay. So, we finally have one equation in the last slide, that is my equation, that k multiplied by k dot E minus k square E is equal to omega square c square with a negative sign k bar bar and then vector E. Now, this equation is a vector equation and should have 3 components. So, we need to figure out which are the 3 components, because that is important. In component wise, if I divide, then there will be 3 equations in our hand, x, y and z. But before doing that, we need to find out what is the x component, what is the meaning of x component of k. So, now we know what is the relationship between D and E. This is the very old equation in the principal axis system. We know that this epsilon bar bar, this quantity, this epsilon bar bar, this tensor quantity can be diagonalized. So, in the diagonal elements are epsilon x x, epsilon y y and epsilon z z. These things can be replaced by k, because epsilon bar bar is equal to epsilon 0 k double bar. This is the relationship between epsilon bar bar and k bar bar we define. So, k bar bar is replaced by this. So, the x component k in the principal axis system, the x component of k is simply kx, which is nothing but the refractive index square along x direction, because kx is equal to n square or nx square. That is an important identity we will going to use. So, once we know the value of k in terms of x, y, z, the next thing is to find out the x component of this entire equation. When you find out the x component of the entire equation, so this equation I put a suffix x, for this equation again I put a suffix x. So, x component of the left hand side, this is a vector equation, the vector quantity. So, whatever we have, the x component will be equivalent to the right hand side x component. Again right hand side is a vector quantity. So, we will have only the x component and then check what is the value. So, if I do the x component, if I try to extract the x component from this equation, then x component of the first part is simply kx and the dot product of this. Please mind that k dot E is a scalar quantity. So, the only vector quantity here is k. So, I will like to take the x component of the vector. So, I will take only the kx from here, and this part is a scalar. So, I need to write kx Ex plus ky Ey plus kz Ez. This portion, the second part of the left hand side containing k square, which is again a scalar quantity. but E is a vector quantity. Once I take the x component, I should write Ex, as simple as that. In the right hand side also minus omega square c square will remain same, because this is a scalar quantity, and then we have the x component of the entire stuff. So, k bar bar x component as shown here in the previous case, that it is just k x x. So, I will write it as k x, and the x component of the E will be E x. So, this equation, which is the equation that is coming from the Maxwell's equation directly in terms of k and E, I now divide this equation, entire vector equation, into 3 parts. First part is the x component, and obviously the second 2 part is y and z component. Then all the x, y, z component of k and E will be in our hand, and then we find that what will happen if I launch the electric field in a particular direction. That means, if the k value is given to you with all the components, then what will happen. Okay. Okay, so the x component, as I mentioned, the x component of the previous equation is this. This is the x component of the previous equation. Now, this x component of the previous equation I can slightly modify, and the modification is the k vector can be in any direction. Since the k vector has any direction, so k vector can be represented by this amplitude and some unit rho. So, if I draw a simple figure here, so this is my x y z component, right, x y z coordinate. Say this is my z coordinate, this is my x coordinate, and this is my y coordinate or y axis. So, now what we will do, we will launch an k, and k will be some specific direction. Suppose this is the direction of k, this is the direction of k. So, x, y, z is our reference or the coordinate system, and I launch a vector k in this particular system, and rho is a unit vector, rho is a unit vector along that particular direction, rho is a unit vector along particular direction. If that is the case, then k can be represented in terms of rho x, rho y and rho z, where rho x, rho y, rho z is nothing but here the vectors, this is y, this is rho z, and this is rho x. What will be the amplitude of the k? We know that k is nothing but omega divided by c multiplied by n, that is the amplitude of k. If this is the amplitude of k, then amplitude will remain same. So, k x amplitude multiplied by this amount and this amount and this amount, where these are the unit vector along 3 directions. Now, rho x, rho y, rho z, since this is the unit vector, so the component square rho x, rho y and rho z, this square will be 1, that is another identity we have. Now, if I replace the amplitude of k with their unit vectors, then I will replace k x as rho x omega square by c square n square, and rho x E x, rho y E y, and rho z E z. This omega square c square is coming because all the cases we have k x, k y and k z. So, k x, k y, k z all have say their corresponding value omega c n. So, omega c n is common, and this k x is something which is omega square c square and n, because another omega square c n is sitting here and we common that. So, that is why the square term is here, and rho x is sitting because here we have kx. Here we have k square. So, k square is nothing but these quantity, because k square is the amplitude of k and square of that. So, this is the amplitude of k and square of that, and then E x as usual, and omega square c square big K x E x. So, now if I simplify this thing by taking E x common here, then I will have omega square c square n square one term, and if I take all this term. So, here one thing, omega square c square and omega square c square all are sitting here. So, omega square c square and omega square c square eventually will be cancel out. Now, if I take E x, then it will be E x common, then it will be E x rho square, and from here we have 1 minus n square, and from here we have 1 k x, and here also 1 n square is sitting here. So, when we divide the entire thing with n square, then this n square, this there will be 1 n square by this and minus 1. So, we will have one equation here, and when we multiply rho x, rho y, rho x, rho z, I will have two equation for E x and E z. So, it will be the equation with, I just write this equation in terms of E x some component, E y some component, and E z some component equal to 0. In the similar way, we can do for y and z component the same equation, because this is merely the one component I am writing in this particular form, but I can do that with other components also. So, if we do the other component, so let us see how it looks. So, this is the previous equation, and now this is the next equation. As I mentioned, if I write in total, what should be the form of this equation? The form of this equation, which is a vector equation, but here this equation is divided into three part: x part, y part and z part. So, when I find the x part, I will have one equation which is this. When I divide to y part, I have one equation which is this, and once I divide the entire equation to z part, z components, so I have another equation like this. These are the looks very symmetric kind of equation. If you do by your own hand, then you will find this is quite simple, and they are coming like a very and similar kind of things will come from y and z. Only just replace, you need to replace this x to y and rho x to rho y and rho y to rho z, something like this. So, this is the equation, this is the form of k that we have already drawn in the previous slide by hand, but here the figure is given that if this is k rho x, rho y, rho z is the corresponding unit vectors along that the direction cosine rather in these directions. So, if these three equation in your hand, now if I launch the k in a specific direction, I should have the value of rho x, rho y and all these things. Then we have the knowledge that how E x will be there. Okay. So, this is my equation. So, let us go back to the next equation, which is the solution. So, what we are doing here, let me go back and say this is there are three equations are here. So, my goal here is to find out the solution of this equation. Here the solution means I want to find out E x, E y, E z. So, in order to find out E x, E y, E z, I need to know the values of rho x, rho y, rho z. That means I need to know in which direction I am basically launching. So, if I know in which direction I am launching, then I can put the value of rho x, rho y, rho z, and then we find out what is my E x and E y. So, let us try to find out the solution. We call this solution 1. So, the solution 1 here is something where we put so here let me now put So, here what we are doing now, if you see very carefully this figure, you will find that my k is lying here along z direction. My k is lying along z direction. If my k is lying along z direction, so that means if I write my rho x, rho y and rho z, I will have rho x is equal to 0 and rho y is equal to 0 and rho z equal to 1, because I am launching my k vector along z direction. I am launching my k vector along z direction. Now, if this is the case, then go back to my previous equation. Here in this equation, I need to put rho x and rho y 0, rho x and rho z, that will also be 0, because my rho x is 0, rho y is 0 and rho z is 1. Why it is that? Because I am launching my k in a preferred direction and that direction is z. So, once I launch my k in my z direction, so I will have the rho x, rho y, rho z value like this. So, rho x, rho y, rho z value, when I start putting this, so I will find that this will 0, this will 0, this will 0. So, I will have one equation, this will 0, this will 0, this will also 0, I will have one equation and another equation. These three equation, if I write from these three equation, when I put the rho x, rho y, rho z value, if I do, then I will have this equation in my hand. I will have this equation in my hand. So, this equation, three equation is now very much simplified equation, and this equation is suggesting that E z has to be 0. E z, so solution 1. So, solution 1, first I am looking for solution 1. So, solution 1 suggests that if I say E z is equal to 0, E y is equal to 0. So, one existing equation is in my hand, that means E x multiplied by k x n square minus 1 equal to 0. So, mind it, k is launched along z direction, E is along this direction, E is now try to actually E I am trying to find out. So, solution 1 suggests that E y is equal to 0, E z is equal to 0, if that is case, but E x is not equal to 0, that is the condition I am putting here in this equation. If that is case, if this is not 0, E z is not 0, then this has to be 0, and from here I find the refractive index value is nothing but root over of k x. That means, along y axis my refractive index will be k x, and the electric field will be in this particular direction, in y direction, in x direction in this case. So, if I launch the electric field, if the direction of my electric field will be in z direction, the electric field polarization will be perpendicular to this. In this case, it is in x direction. So, now it will start propagating over this, and the polarization of E will remain constant. There will be no change in the polarization, E will be E, that is one issue. Second thing very interesting, that even in anisotropic system, if I launch k vector in my z direction, then E and k remain perpendicular, which was not there in the previous general case, which was not there, that E and k was not perpendicular to each other, but here we find that if I launch my E vector along z direction, the E vector can be perpendicular to the k. So, this is solution 1. So, now try to find out what is solution 2. If the solution 1 is there, so it seems that there is another solution, and this another solution is solution 2. The solution 2 is again there is nothing new, only I say that E z is equal to 0 because this equation is consistent with that, and before I put E y 0, now I am putting E x equal to 0. There is no x component of the E. So, since there is no x component of the E, we have only non-zero component along y direction. So, that means electric field is now along y direction. If electric field is now along y direction, so what happened? The polarization again remain conserved. E will be propagating the polarization of the E will be in this direction, and it is perpendicular to the k, and they are propagating without any kind of change of his polarization. So, these are the two solutions I find out. So, here I like to stop because solution 3 is still possible, and we will find out what is the solution 3. In solution 3, what we will do in the next class, that we will take E x and E y both non-zero. If we take this thing both E x and E y non-zero, we will find some interesting fact. So, we will do that in the next class. So, here we will like to stop. So, today we will learn in anisotropic system how the E x and E y, these components, if I launch the electric field along z direction, then what happened? The polarization of electric field along one direction, that means perpendicular to that z direction, that means x and y, the polarization remain intact. So, these are the two solutions, we are getting, but as I mentioned, we will get from this equation we can get more solutions. So, solution 3 is still possible, so we will find out what is the solution 3. So, thank you for today's your cooperations and your attention. So, let me stop here. So, next day we will start in the next class we will start the light propagation problem exactly where we stop here. So, solution 1 is there, solution 2 is there. So, I will start from solution 3. With this note, thank you very much and see you in the next class.